Okay, now we're trying to start calculating that critical load that we discussed, that if your applied load, the compressive applied load, gets bigger than this limit that you have, your column is susceptible to buckling and you should ignore it. Now, in order to calculate this, as the assumptions mentioned, in this case, I'm taking a column which has pin at its both ends. Exactly the column that we saw. And due to the loading applied to it, it will buckle something like this. You can see a lateral deformation over here. Remember this, all of these are happening in elastic states. We have not entered in elasticity. No permanent deformation, nothing like that. The moment that I remove my applied load P, everything will go back to its normal situation. This P prime that you see at the bottom is the reaction due to this P that is applied. I have defined two axes for my column. X-axis is going from point A all the way to point B, making the length of my column L, and Y-axis goes from A to a lateral deformation side, yes? So you can see if this is the axis, there is some Y movement over here. If I give the coordinates, this will be x0, y0, point A will be x0, y0, and if I still continue with the coordinates, again point B will be y0, as you can see, axis y is 0, and x will be L. Now, as we discussed, following the Euler's theory, instead of looking at the stresses due to this P, I look at the moment stresses. Because of that, I'll do a section at point Q. Yeah, point Q is just a random point with a distance of x and distance of y. Yeah, so I can get the coordinate of this point at this location. And I'll just take it out. Yeah, let's do a summation of moments at point Q. So summation of all moments at point Q equals to 0. As we discussed, we are in equilibrium, so everything should be 0. So I have a moment over here which it's against my direction at point Q, so I'll put minus m. Yeah, and then this P prime, if you remember, moment was force times the perpendicular distance, doesn't have any distance to point Q, so P prime will be 0, no moment due to that. But this P which is applied, this P which was my compressive axial load, has a distance y to Q, has a perpendicular distance of y to Q. So this will cause a moment. Now, if I follow this force with the centroid of Q, it's anti-clockwise, while my positive direction is clockwise. So this will be minus P times its perpendicular distance, which is y. Any other force? No. So this will become 0. And then from this, I can conclude that negative m is Py. And then from this, I'm sure you all will agree that m is negative Py. I just took this negative to the other side, considering this direction as positive. So this m over here is actually negative opposite direction of P times y. Yeah, we're happy with this. Okay, now let's continue this. From the other side and from previous lectures, we had proven that there is something called elastic beam theory. And if you remember, we had a name for it, stress me every year I run. And we were discussing that in different situations and different scenarios, we'll take some of this formula and we'll try to help us solve some problems. In this case, I'm just concentrating on these two bits. So moment, elastic modulus, which represents the material, second moment of area, which represents the, let's say, the cross section, and r, which was the radius of curvature. On the other side, we have proven that 1 over r, so the inverse of radius of curvature, is actually the second differentiation of y over dx2. Yeah, we have proven these in the lectures for deflection. Now, what happens if I replace this R with this? So, do you agree that R can be equal to these guys? And I'm just replacing these with that. How does it work out? It will be second differentiation of y equals to m, and these two come out together, ei. Now, what if I replace this m with this negative py? So this equals to negative py ei. So on one side I had this formula, on the other side I had the elastic beam theory, and on one side I had proven that that m at that point that I had is equal to this. So I just took 1 and 2 and 3 all together to conclude this. There is a y here, there's a y here. So let's simplify this a little bit further as well. So I can write y over dx2 plus, I'm taking this to this side, so p ei y equals to 0. To simplify it, remember this is capital P, which was the applied load. I will say the whole thing of this, I call it small p. So my formula now will become 2y dx2 plus small p to the power of 2y equals to 0. So I just did some assumptions that P2, small p2, is actually capital P over ei. And I ended up with this. So very quickly we managed to prove that second differentiation of y plus a small p2y equals to 0. From elastic beam theory, from the moment that we got, and the curvature, radius of curvature. If you look at this and you look at the differential equation of simple harmonic motion, simple harmonic motion is something like this: dop, 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 like a pendulum going left and right, left and right. If you look at the differential equation of simple harmonic motion, it looks exactly like this. So instead of p to the power of 2, it might have a w, or omega to the power of 2y equals to 0. People have proven, and this is not part of our lecture, that the solution of this, if you make it equal to 0, the solution of y is such a formula. So the general solution for such differential equation, meaning such differential equation, is this. This is the small p that you have. And if you remember, P2, as we assumed, was capital P over EI. Yeah, so this is the P2 that we have over here. I just assumed the whole thing as P2 for simplicity to make it look like a differential equation of simple harmonic motion. And now I'm saying that the solution of this differential equation is this. People have proven that. Yeah. Now, in order to get exact numbers of y, I can go back to the boundary conditions that I had. So I had a column something similar to this. So there was a pin at the top, point A, and there was a pin at the bottom, point B. This was, as you remember, x0 in terms of coordinate, and this was x equal to L in terms of coordinate. Because the whole length of my column was L, so I started with an axis of 0 all the way to the axis of L in terms of coordinates. Now, similar to what we have done in, let's say, displacement, I'm putting the boundary condition. So I say if x equals to 0, so I put 0 here and 0 here, yeah, everything will become 0, yeah? So this gives me b is equal to 0. Remember this, cosine of 0 is 1 and sine of 0 is 0. So if I put 0 over here, this bit will become 0. This cosine of 0 will become 1. So y will become equal to b, and I have already said that y is 0 because there wasn't any displacement at this point and at this point. So because there's no displacement, that means b is equal to 0. So the whole of this bit will be omitted. Now let's use the other boundary condition. This time I'll put x equals to L. Again, I don't have any displacement, so I'll have an equation which says y is equal to 0, a sine of PL. And I have already concluded that b is equal to 0, so I won't bother with this side. So again, I'll put y equal to 0 because at x equals to L, my displacement is 0. And I have put x equal to L over here, so it will be 0 equals to a sine of PL. Two solutions. One concluded that b is 0, the other one concluded that 0 is equal a sine of PL. Now, in order for this statement to be true, either a should be 0, and the whole thing will become 0, and that means that my column, if a is equal to 0 and then y is equal to 0, the column is straight with no deflection, yes? But this wasn't my case. I saw that my column did something like this. I saw that there was a deflection. I saw that there was a movement in y direction. So the first one is not true. So a cannot be 0. If sine of PL equals to 0, then PL is a number and n times pi due to the trigonometry relationship. So look at like this. Sine of pi is equal to 0. Sine of 1 pi is equal to 0. Sine of 2 pi is equal to 0. All the way to sine of n pi's is equal to 0. So in order for this to be true, PL should be equal to an n pi. Now that n can be 1, 2, 3, all the way to millions of pi. So from all of these boundary conditions, we concluded this. Now let's take this out and let's consider this that we had as well. Over here, I had assumed that p, the small p to the power of 2, is capital P over EI from the previous thingy. Now I have concluded that p times L is equal to a number of pi's. Let's bring these two out and let's see whether we can get a relationship between them. So, as we said, we have small PL equals to a number of pi's. On the other side, I have this as well. So do you accept that P, in this case, small p, will be square root of capital P over EI? Yeah. Can I conclude from these two that the square root of my axial force applied over my material times the cross-sectional representatives times the L that I have here is n times pi? Let's take like a power of 2 on both sides. So will be like P EI times L to the power of 2 equals to n to the power of 2 times pi to the power of 2. Let's sort it out for P. So in this case, my P, my capital P, which was the actual force that I applied, will become something like this, EI divided by L to the power of 2. This is accepted. Now, the smallest value of P, which is the critical load, yes? So imagine you have the column and you have a P applied to it. You want to know what is the smallest possible PCR to be the limit, yes? Your limit should always be the smallest one. You can't say, my limit is 20, but I consider 30 as well. Then what happens if this applied P is 24? For sure you will fail. So in order to have the smallest value of P to be our P, like critical load, N should be 1. Due to, again, the trigonometry relationships. So if I put 1 over there, my P critical will become pi to the power of 2 E I divided by L to the power of 2. This expression is known as Euler's formula, and this is the critical load that you have. So very simple, by just looking at the moment caused due to that deflection. If you remember, we had a P, we calculated this moment, we went through the beam theory, elastic beam theory, radius of curvature, then we looked at the formula and we said, oh, it looks very similar to the simple harmonic motion. What is the, let's say, the solution to that simple harmonic motion? It was y. Then we used some boundary conditions in order to conclude some states, and then we got to this point and we reached to this point. So this is the critical load. This is the formula for critical load of a column which has the condition of pin-pin. So one pin at one end, one pin at the other end. Pin-pin with an axial load applied to it. Now, if this axial load is bigger than PCR, the critical load, there is a high chance that your column will buckle before even reaching yielding, because again, we're all in elastic state. We have not passed the yielding point. And on the other side, let's look at this formula. The critical load depends on columns' geometric properties. Yes, so I and L, yes, the second moment of area as well as the length of the beam, and cross-sectional shape, which was the second moment of area, the column length, and the column's material. E is the material of my column. So the stronger my column is, my critical load limit goes higher. The better and the bigger second moment of area I have means I have a much stronger cross-section. My critical load goes higher. The more slender and the more long my column is, my critical load will go lower. And as you can see in this formula, there is nothing related to stress, the yielding stress, anything of like the strength of material or anything like that. It's only a representative of material, which can be steel, timber, reinforced concrete, anything, the cross-sectional shape, and how long the length of my column is.